Hello, welcome back to Andrews Learning Center's Organic Chemistry series. Today we're going to talk a little bit about atomic structure and bonding. To begin, I would like to give a brief refresher on the structure of an atom using the Bohr model. So an atom contains protons, neutrons, and electrons. A proton is a positively charged particle found at the center or the nucleus of an atom. A neutron is a neutral molecule, as the name suggests, that's also found at the nucleus of an atom. Together, the protons and the neutrons make up the atomic mass of the atom. Electrons are negatively charged particles that are found orbiting the nucleus. The electrons are often found in what we call the electron cloud. In the Bohr model, electrons are found in rings outside of the nucleus. Electrons follow the octet rule. So that means in these rings, the first ring around the nucleus has 2 electrons, but every other ring outside of that has 8 electrons. For stability purposes, an atom will often do what it can to have a full octet, whether that is lose or gain an electron. So that was a brief refresher on the Bohr model and the octet rule. And there's more to it than that, but I just wanted to go over that topic quickly. So while the Bohr model is extraordinarily helpful and helps students learn and understand about the electrons in the electron cloud, which are represented by rings, in reality, the structure of an atom is much more complicated than that. There are areas with high probability distributions of likelihood that an electron will exist. These spaces that an electron could very likely be in are called orbitals. These orbitals can take very complex shapes. Orbitals are typically designated by letters. For example, there is the s orbital, there is the p orbital, and there are orbitals with extraordinarily complex shapes like the d and f orbitals. So looking more deeply at the orbitals, the s orbital is in the shape of a sphere. The p orbital is in the shape of a dumbbell, and you can see the more complex orbitals as well. The shapes of orbitals are a very important characteristic that goes along with orbitals. However, there is more to it than that. Electrons have shell numbers, which are essentially the energy level associated with the electrons in that orbital. It's also greatly correlated with the distance away the electrons are from the nucleus. So let's look at 3 different orbitals with 3 different shells. 1s2, 2s2, and 3s2. The electrons in 2s2 are greater in energy than the electrons in 1s2. Likewise, the electrons in 3s2 are greater in energy than the electrons in 2s2. You can also see that the size of the orbitals increase as the shell number increases. So you may be thinking to yourself, wow, this seems like a lot of general chemistry. I came here for organic chemistry. And don't worry, we're going to get there. It's very important that you understand the concept of orbitals and electrons in the outermost orbitals to understand how atoms will bind to each other. And chemical bonding is a huge part of organic chemistry. Okay, so back to orbitals. So the electrons in the outermost shell and the outermost orbital are the most important. They give atoms characteristics such as stability, and they kind of dictate how an atom will bind to another atom. So there are multiple types of chemical bonding. For example, there is ionic bonding, when an atom wants to transfer an electron to another atom, and that allows for the electrostatic interactions between the 2 atoms. For example, sodium chloride, where sodium has transferred an electron, making it positively charged, and chlorine has accepted an electron, making it chloride, the negatively charged ion, and their electrostatic interactions allow them to bind together. So that's an example of transferring an electron, an ionic bond. When atoms share an electron, this is called a covalent bond. Their orbitals can take very complex hybrid shapes between the 2 atoms. This is called hybridization. So these complex hybrid bonds and new shapes lead to complex geometries for the compound's bonds. For example, there is a linear geometry, a trigonal planar geometry, and a tetrahedral geometry. All of these geometries have different bond angles. The type of hybridization a compound exhibits is based on the number of groups or regions of electron density surrounding the central atom. For example, if there are 2 groups, the hybridization will be sp. If there are 3 groups, the hybridization will be sp2. And if there are 4 groups, the hybridization will be sp3. So as you can see, based on the number of groups, we're sequentially moving up from letters S to P and sequentially increasing the amount of P's. There are even more complex hybridizations that can be found. An example, just to drive this point home, is methane gas. So methane gas has a central carbon and 4 hydrogens covalently bound to that carbon. So the carbon has 4 groups around it. So that means this methane gas will be sp3 tetrahedral. Another example is carbon dioxide. So carbon dioxide, or CO2, has a central carbon and 2 oxygens bound to that carbon. So carbon dioxide has 2 groups around the central carbon, meaning it takes a hybridization of sp. So that's it for today on atomic structure and bonding and hybridization. So that's the end of the video. Don't forget to like and subscribe, please. Don't forget to check out our Instagram. It has a lot of cool scientific videos that you may enjoy. And also definitely don't forget to check out our interactive learning platform, andrewslearning.com, where you can take some of the material you learned today and learn it more in depthly in an interactive and engaging way. Okay, take care.